students, in the last lecture we have discussed about the energy of an electron in the different states of hydrogen and hydrogen like atoms. So, now we will discuss about a few terms which we will be using further in this chapter. Let us get an idea about what those terms are. So, first of all, ionization energy. So, ionization energy is basically the amount of energy that should be given to an electron, to a gaseous atom for an electron which is in the ground state, to remove it completely from the bounds of that particular atom. So, to simply put, it is the energy required by an electron in ground state of a gaseous atom to move to n is equal to infinity. So, from n is equal to 1 state, to take the electron from n is equal to infinity state in a gaseous atom, the amount of energy that should be supplied is what we call as ionization energy, and it is generally represented in electron volts. It is measured in electron volts. So, that is ionization energy. So, the next term which we will be using is ionization potential. Okay. So, ionization potential is something which is related with ionization energy. So, we can, as you can see the term potential here. So, it basically means the potential difference through which an electron should be accelerated, so that it gets an energy equal to ionization energy. So, that is what we mean by ionization potential. So, for example, we all know that the ionization energy for an electron in hydrogen is equal to 13.6 electron volts. So, to remove an electron from the ground state of hydrogen atom, we need to supply the electron an energy of 13.6 electron volts. So, what ionization potential means is that, so to give an electron 13.6 electron volts of energy, through how much potential difference should that electron be accelerated. So, we all know that the kinetic energy imparted can be directly written as E into V, where E is the charge of the electron and V is the potential difference through which it is accelerated. So, we can basically define by using this idea that ionization potential is nothing but ionization energy divided by E. So, which means in this case the ionization potential for an electron in hydrogen is nothing but 13.6 volts. So, it is just the ionization energy divided by E. So, and the definition, I will write the definition here. The potential difference through which an electron should be accelerated so that it gains ionization energy. Okay, so that is the definition for ionization potential. Now, similarly, we can also talk about another term called as excitation energy. Now, you all know what excitation means. Excitation means taking an electron from a lower energy state to a higher energy state, and excitation energy means exactly that. It is the energy required to take an electron from a lower energy state to a higher energy state. So, this definition is, I will just write a simplified expression here: energy of the higher state minus energy of the lower state. So, that difference in energy is what we call as excitation energy. So, when we talk about excitation energy, for example, let us consider that we have an atom, a hydrogen like atom, So, these representing different orbits. Now, let us consider that there is an electron in the second orbit. So, in n is equal to 2 state. So, if there is an electron in the n is equal to 2 state, so we can say that this electron can, when given energy, it can move to 3 n is equal to 3 state, or it can move to n is equal to 4 state. So, the smallest energy with which we can excite the electron, we call that as first excitation energy. So, first excitation energy. So, if for example, if I consider an electron which is in the ground state, for an electron in the ground state, first excitation energy means 1 to 2. So, first excitation energy is basically the energy needed to move the electron from n is equal to 1 to n is equal to 2. So, that is basically how we define first excitation energy. Similarly, we can also understand second excitation energy and so on. So, energy required to transition an electron from a lower energy state to a higher energy state. Now, similarly, just like the earlier scenario, we can also define excitation potential. And excitation potential is nothing but the potential difference through which an electron should be accelerated so that it gains that excitation energy. For example, if there is an electron which has an excitation energy of, let us say, some 10.2 electron volts, so we can directly say that the excitation potential is, how much would that be? Just 10.2 volts. So, 10.2 volts is the potential difference through which the electron should be accelerated so that it gains 10.2 electron volts of kinetic energy. So, that is the basic idea about energy and corresponding potential. And apart from this, there is one more definition which we will be generally dealing with, and it is called binding energy. So, generally you will be coming across this term of binding energy of an electron in a particular orbit in a particular atom. So, you have to know what that term basically means. So, it basically suggests the amount of energy that is required to remove an electron from any state in which it is present. So, unlike ionization energy is defined for an electron which is in the ground state. So, the energy required to move the electron from n is equal to 1 to n is equal to infinity is what we call as ionization energy, whereas binding energy can be defined for an electron which is in any state. So, we can say that for any electron in its initial state, let us call it as n, the energy required so that it can move to n is equal to infinity is what we call as binding energy. So, from any state you can also define binding energy for an electron which is in n is equal to 3. So, whatever is the energy required to take it from n is equal to 3 to n is equal to infinity, completely remove it from the atom is what we call as binding energy, right. So, can you tell me what would be the binding energy of an electron, let us say. So, binding energy of an electron in n is equal to 2 state of, let us consider He plus. So, what is the binding energy of this electron? So, let us find the value of that. So, we can directly write the expression here as when the electron is in this particular state, let us calculate its energy first. So, we need to find the binding energy. I will first find the energy of that electron in the second state, n is equal to 2 state, and then I will find the energy of the electron at the infinity state. So, you all know that the energy of electron in infinity state would be 0. When it is completely removed, its energy becomes 0, and when it is in n is equal to 2 state, what is the energy that this electron in He plus. So, the electron in n is equal to 2 of He plus, how much energy does it possess. We already have an expression for that, minus 13.6 into z square by n square. Z is 2, so 2 square by n is also 2, so 2 square. So, minus 13.6 into z square by n square. So, now when I simplify this, I get the value as minus 13.6 electron volts. So, that is the energy of the electron in the second orbit of He plus. Now, how much energy should I give to that electron so that it can be taken to infinity, which means you have to change the electron from this energy state to this state. It means that I need to supply the electron with an energy of 13.6 electron volts. So, that 13.6 electron volts will be the binding energy of this particular electron. So, we can directly write binding energy is equal to 13.6 electron volts. So, that should be the answer. Now, let us talk about absorption spectrum. You might have heard of this term. So, what it basically means is that, so whenever we have a sample of a particular gas, let us consider atomic hydrogen. So, when I have a sample of atomic hydrogen and when light is incident on that hydrogen atom, hydrogen gas in this particular case. So, what happens is that if this incident beam has different kinds of wavelengths, so all combination of many wavelengths. Now, these different wavelengths, when they pass through this hydrogen gas or atomic hydrogen, and when they come out onto the other side, as they pass through and just come out on the other side. So, when these wavelengths come on the other side, now when you collect these wavelengths which come out of this and when you observe these wavelengths, what happens is that you would observe that some wavelengths are missing. And the reason why some wavelengths are missing is because these atoms which are present here, so these atoms would have absorbed some of the wavelengths or energy corresponding to some of the wavelengths present over here. And the reason I have told you earlier also, the electrons in a particular atom can only absorb few kinds of energies. It cannot absorb all the energies which are incident on that. Only it requires only those energies which are required for excitations, and those are very specific. Those are equal to difference between the energy levels. So, it can only absorb specific wavelengths, and that is the reason out of the multiple wavelengths of light which is incident on this gas, we can say that only few wavelengths will be missing on the other side, and the collection of all those missing wavelengths which were actually absorbed by the gas. So, that collection of missing wavelengths is what we call as absorption spectrum. So, that is the basic idea. Let me write it down. When non-monochromatic light is incident on a gas, some wavelengths or energy corresponding to some wavelengths are absorbed by the gas, absorbed by electrons in the atom. And what do they do with that absorbed energy? They get excited for excitation. So, as a result of that, so those absorbed wavelengths would be missing in the light which is coming on the other side, and the collection, those we call them as dark lines. So, when you see this on a electromagnetic spectrum, you would observe that there are all wavelengths of different colors present, but there will be dark lines near the wavelengths which are already absorbed by the atoms. So, those collection of dark lines, so the dark lines appear in absorption spectrum. And what do those dark lines signify? So, those dark lines basically signify the absorbed wavelengths. So keep in mind that whenever you are talking about, whenever you come across the term absorption spectrum, you should automatically connect it with excitations. So the electrons have used those wavelengths for excitation from a lower energy level to a higher energy level. So that is what we mean by absorption spectrum, and absorption and excitation are one and the same. Now similarly, now you can guess what emission spectrum means. So when we now talk about that, so emission spectrum. So when we consider a gas which is excited, electrons are in the higher energy state. So those, we have already discussed that the electrons cannot stay in that excited state for very long. So the de-excitation will be very instantaneous. So an electron in an excited state stays there for a very short duration. And the value of that is also approximately somewhere around 10 power minus 8 seconds. So which is a very, very small time. So even if an electron excites to a higher energy level, it won't stay there for long. It immediately loses that energy in the form of a photon and it comes back. And while coming back, while it is getting de-excited, so that energy is released in the form of a photon, in the form of electromagnetic wave. And the wavelengths which are released during de-excitation. So the collection of all those released wavelengths during de-excitation is what we call as emission spectrum. So I'll write it down here. It is basically the collection of emitted electromagnetic waves during de-excitation of an electron. So that is what we mean by emission spectrum. So an electron in the higher energy state loses energy and comes to the lower energy state, and that difference is released in the form of a wave, photon. So the collection of many such wavelengths is emission spectrum. Okay, now let us understand, while we have an emission spectrum of a particular gas, let's say that there are multiple energy levels like this. So we have already discussed that the energy level differences would become lower and lower as we go up. Okay, let us consider, let's say it is hydrogen only. This has the n is equal to 1 state, n is equal to 2 state, n is equal to 3, n is equal to 4, 5, 6, so on. Now let us consider an electron which is, let's say, in the 4th state, or let's say 5th state. Now this electron which is in the 5th state is now about to de-excite, and it can come to the lower energy levels in many different ways. So now we are going to discuss about how many possible wavelengths might be emitted in the emission spectrum of a particular excited state. So if I consider that the excited state here initially is n is equal to 5, so from n is equal to 5 state, if this electron is trying to come back to another lower energy state, how many different ways can it come down to? So one important thing which we will have to keep in mind here is that whatever analysis which we are doing here is for a sample of gas which has a bulk of atoms. So there are large number of atoms present, and if I consider that all those atoms are initially in the, let's say, 5th excited state, I am just taking an example. So there are many there are many electrons initially in the 5th excited state, let's say. So this particular energy level, there are many electrons. Now when these electrons try to come to lower energy states, so we can say that there are many possible ways in which these electrons can come. And let's say if this electron directly jumps from 5 to 1, this electron may jump from 5 to 2, and this electron may jump from 5 to 3, and this one from 5 to 4. Similarly, if I consider the other electrons also, so which are initially in the fifth state, so these electrons which are initially in the fifth state will undergo one of these transitions. So there are four possible ways in which an electron can move from the fifth state downwards. So from fifth state, there are four possibilities. Now, in this process, we can say that during the de-excitation, some electrons will come to the fourth state as well. So we have seen that this electron has come to the fourth state. So because there are there are large number of atoms, so there will be many such electrons which will come to the fourth state as well. So now, let's say there are some electrons in the fourth state also. Now let's see what are the options those electrons will have while de-excitation. So now if I consider this electron in the fourth state to directly de-excite from 4 to 1, this electron may de-excite from 4 to 2 and this electron may de-excite from 4 to 3. So as you can see here, for the electrons which are in the fourth state, so these three electrons, I have marked those three electrons. So these three electrons have three possible options. They can directly jump to 1, they can jump to 2, they can jump to 3. So which means from fourth state, these electrons are having three possibilities to de-excite. Now we can do the same logic. We can now talk about the third state. So definitely there will be few electrons which would reach the third state, and from third state they will once again try to de-excite. And how many possible wavelengths can they emit? An electron in the third state can directly jump to 1, an electron in third state can jump to 2. So there are no other possibilities. So from third state we can say that there are two possibilities, and you can actually see a pattern here. So we can say from second state there is only one possibility. So now if I ask you, if I consider the electrons which are initially in the fifth state and if they now start de-exciting, what are the total number of wavelengths that I can observe in the emission spectrum? Because remember, if there is a possibility, then there is a chance that it will definitely happen. We have to consider that it will happen because we have a large sample size. We are taking a bulk of gas, which means there are large number of atoms in that particular gas. So if there is a possibility of something to happen, we should consider that it will happen. So if I just find out how many possible scenarios are possible, I can just say that that will be the number of photons that I can observe in distinct photons which I can observe in the emission spectrum. So they can ask you a question like this: how many different wavelengths can be observed in the emission spectrum for a gas which is initially having electrons in the fifth state? So the answer for that would be 4 plus 3 plus 2 plus 1. So in total we have 10 different photons emitted. So each of these transition corresponds to different energy. So none of these transitions, none of the lines which I have drawn here, including 2 to 1, so none of the lines which I have drawn here has the same energy difference. So which means they have all different wavelengths also. So in this particular case which I have taken for transition from fifth state to below, there are 10 possible transitions that can occur. So there are 10 possible wavelengths or 10 wavelengths in the emission spectrum. So we can also generalize this into a formula. So if I consider that if the gas is initially, if the gas is in the nth state, or let's say if the electrons are in the nth state. So if initially the electrons are in the nth state, so now you can easily answer, then the number of different wavelengths emitted is equal to. So try to think about that. I'll just discuss now. So let's see. So from nth state, so if the electron is initially in the nth state, so how many possible ways can it come to a lower state? So we have just seen that from fifth state, if it has 4 possibilities, then from nth state we have n minus 1 possible ways. And similarly, so from, if I consider an electron in the n minus 1th state, then from there I will have n minus 2 possible ways and n minus 3 possible ways, so on till 1 possible way, which is 2 to 1. This corresponds to 2 to 1 transition. So just like we have got there. So these are the possible ways in which the transitions can occur from nth state downwards. So when I add all these to find the total number of possible ways or transitions that can occur, I will be getting a series like this: 1 plus 2 plus 3 plus so on plus n minus 1. And I guess you are all aware of how to find the sum of this series. So we can directly write it as n minus 1 into n minus 1 plus 1 divided by 2. So this would be the sum of that particular series, and the value of this would be n into n minus 1 by 2. Okay, so I will just summarize what we have just seen here. It means that if the electrons are initially in the nth state, if all the electrons are initially in the nth state, and if you observe the emission spectrum of such a sample of gas, so in that emission spectrum we can observe n into n minus 1 by 2 different types of wavelengths. So that is the basic idea. Now let us also think about, so whatever we have discussed is for a sample of gas. Sample of gas means there are large number of molecules, atoms, and if there is a possibility of something to happen, we will consider that it will happen. So we have seen that n into n minus 1 by 2 is the number of different photons that are emitted from a sample which is initially in the excited state, in the nth state. Now similarly, let us find out how many possible photons can be observed from an excited state when I consider only a single atom. So when I have a single atom, so let us say, let us take the same example as earlier. So let us say the electron is initially in the fifth state. What are the possible ways that are present for a single electron? It can directly go from 5 to 1. Yes, it can directly go from 5 to 2, then 2 to 1. So it can go from 5 to 2 and later from 2 to 1, or it can go from 5 to 3, which is this. It can go from 5 to 3, 3 to 1, or 5 to 3, 3 to 2, 2 to 1. So I will just write it down here. So the electron can go from 5 to 3, and from after 5 to 3 it can go directly from 3 to 1, or it can go from 3 to 2 and then 2 to 1. So now try to think of it this way. So if I look at it this way, so now what I am asking you here is, as this electron de-excites eventually to ground state, to the stable state, so as it de-excites and reaches the ground state, so there are many things that can happen even with this single electron. It can choose any one of these ways of de-excitation. Now the question which I am asking you here is, what is the maximum number of de-excitations that are possible? See, if you choose this, there is only one de-excitation and there is only one photon that is emitted. If you choose this, which means 5 to 2 and then 2 to 1, there are two possibilities. So in that manner, what is the maximum number of photons that can be emitted while the electron gets de-excited to the lower energy level? So you can take a guess. So if let us say this is 5, this is 4, 3, 2, 1. So we can easily say that the maximum number of steps through which it can go through by the time it reaches 1 is by taking one step at a time, like this. So if it goes like this to next successive lower energy level, so it can take more number of steps, and each step there, each transition there corresponds to a photon. So in this particular case, you can see that the electron in the fifth state can reach the first state through a series of 4 transitions, and that is the maximum number of transitions that it can take, because there is only single electron. We should only count this as the possibility. So we can say that in this case, because there are 5, it is initially in the 5th state. So an electron in the 5th state can take 4 transitions to reach the ground state, and that would be the maximum. So can take a maximum of 4 transitions to reach ground state. Now, if I generalize this result, if the electron was initially in the nth state, so if it was initially in the nth state, so I can easily say that n minus 1 is the maximum number of photons that can be emitted. So n minus 1 will be the maximum photons that can be emitted. Right? Now, let us talk about hydrogen spectrum. So, basically we will be discussing about the different transitions and different photons that are emitted whenever those transitions occur in a hydrogen atom, and what type of energies are released during that process. We can actually group them into different sets. So, we will be learning about that now. So, for that, let me just draw the energy level diagram first. So, I will take this as the ground state. You all know that this can be considered as 13.6 minus 13.6 electron volts. So, the second state, okay. Let us take energy levels up till here. So, this corresponds to n is equal to 1, n is equal to 2, 3, 4, 5 and 6. Let us consider till here. Now, so here if I consider different transitions that are happening in a hydrogen atom, we all know the energy levels as well. This is minus 13.6, this will be minus 3.4 electron volts, this will be minus 1.51 electron volts and so on. Okay. So here if I consider the transitions that are occurring to the ground state, with the final state as the ground state, if I consider all possible transitions that are occurring, so let us say the transition corresponding to 2 to 1 or 3 to 1 or 4 to 1, 5 to 1 or 6 to 1, so on. You can also consider this level as infinity. So here we have n is equal to infinity, which corresponds to an energy of 0. So you can also consider infinity to 1. So all possible transitions from any higher state to the first state. So all the group of all these transitions, the collection of all these wavelengths, we call these as the Lyman series. So this is in a hydrogen atom. I am talking, whatever I am telling now is for a hydrogen atom. So collection of all the wavelengths of light which is emitted from a higher energy level to the transition to the lower energy level of n is equal to 1 is what we call as the Lyman series. Now similarly, if I consider all possible transitions from a higher state to the second state, so n is equal to 3 to 2 transition, 4 to 2, 5 to 2, 6 to 2 and similarly infinity to 2. So the collection of all these wavelengths, so we call this as Balmer series. And similarly, if I consider a similar scenario for the third level, so 4 to 3, 5 to 3, 6 to 3 and infinity to 3. So I have not drawn all the energies in between. So you can consider this is valid for every transition in between 6 and infinity also. Okay. So the collection of all these is called as Paschen series, and similarly 5 to 4, 6 to 4, infinity to 4. So this is called as bracket. And so all the transitions to n is equal to fifth state from any higher level is called as Fund series. Okay. So this is how we group them into different wavelengths. So now if I try to analyze this particular transitions and these wavelengths which are released during those transitions. So here we can observe one important thing. Let me just consider one series here. Let us consider this Balmer series. So if I consider Balmer series, so let us analyze Balmer series first. So in Balmer series, can you tell me, can you think of what would be the highest energy? Which transition corresponds to the highest energy and which transition corresponds to the lowest energy? So highest energy and lowest energy. So you can easily guess that. So highest energy corresponds to infinity to 2 transition and lowest energy corresponds to n is equal to 3 to n is equal to 2 transition. So here we can say that this corresponds to infinity to 2 and this corresponds to 3 to 2 transition. Okay. Now based on this, if you actually calculate the values, we already know the energy also for this transition. We can see that here itself. So infinity to 2 transition will have, this is 0, the energy here is 0 and here it is minus 3.4. So 0 minus 3.4 and the value of that would be 3.4 electron volts. So 3.4 electron volts is the highest energy in the Balmer series. And similarly, what is the lowest energy? Lowest energy corresponds to the transition from n is equal to 3 to n is equal to 2 and the difference is 1.51 minus 1.51 minus 3.4. If you find the difference, it would be 1.89. Let us calculate 3.4 minus 1.51. So 9, 1.89. So 1.89 electron volts. So that would be the lowest energy in this Balmer series. Now the reason why I have found the values of energy here is because I want you to show that these energies will actually lie in the visible region. You all know the visible range. So the visible range corresponds to wavelengths varying from roughly 400 nanometers to some 760 nanometers. So when you look at the energies of these wavelengths also, so this is roughly around 3.1 electron volts and this one corresponds to an energy of roughly some 1.6 electron volts. So what we need to observe here is that, so the Balmer series, all the wavelengths corresponding to the Balmer series or almost all the wavelengths corresponding to the Balmer series will have their energy lying within the visible range, which means we can actually see that light coming from the Balmer series of a hydrogen atom. So that is what it means. So we can consider that this Balmer series lies in the visible range. And if I consider the Lyman series has its lowest energy. So for Lyman series, lowest energy is this 2 to 1 transition, which is 10.2 electron volts, and the highest energy is always infinity to the lower transition. So the highest energy here corresponds to infinity to 1 transition, which is 13.6 electron volts. So what I can say here is that, so when I consider Lyman series, so for Lyman series the range of energies which it has is far away from the visible range. So, visible range only contains photons of this energy 1.6 to 3.1. So, it is higher than that energy level. So, we can say that Lyman series actually lies in the ultraviolet region. So, all these photons basically correspond to UV rays, and almost all these wavelengths correspond to visible range, and this correspond to, these are energies which are lesser than the visible range, they are below the visible range in energy and higher in wavelength. So, these correspond to infrared rays and so on. Okay. So, now similarly here there are few terms which we will be using generally while talking about these series. They will be talking about this term called series limit. So, they will be asking you to find out what is the series limit for Lyman series in hydrogen or He plus or so on. So, we will need to know what is series limit. So, series limit basically means the wavelength or the transition corresponding to the maximum energy in that particular group. For example, if I consider this Balmer series, so the series limit of Balmer series would be the one with the highest energy transition, and the highest energy transition here would correspond to n is equal to infinity to n is equal to 2. So, for any series we can say that the series limit corresponds to the transition with the highest energy. So, as simple as that. So, for example, let us say if I ask you what is the wavelength of, what is the series limit wavelength of Paschen series, if let us calculate that, let us take it as a question. So, what is the series limit wavelength in Paschen series? Okay. So, to calculate that Paschen series, I know that all the transitions will be to n is equal to 3 state, from a higher state to n is equal to 3 state. So, series limit basically means the transition from infinity to that particular state. So, we can, by looking at this, we can easily understand that we need to basically understand the transition n is equal to infinity to n is equal to 3. So, we need to find out the wavelength of this particular transition, the photon released from this transition, n is equal to infinity to n is equal to 3, and we already have a formula for finding the wavelength during these transitions, the Rydberg formula which we derived earlier. So, we can directly write 1 by lambda is equal to r into, let us consider hydrogen atom itself. So, okay, Paschen series means hydrogen atom. So, Z will be 1 here. So, r into 1 by 3 square minus 1 by infinity square. So, that is the expression we get, and solving this you would see that the value of lambda is equal to 9 by r. So, that would be the series limit of Paschen series. So, that is what it means. So, you need to have a broad idea so of which range do each series belong to, and what do they represent, what energies lie in that particular series. So, as you can see, Lyman series mostly contains UV rays, and Balmer series mostly contains visible rays, and Paschen IR rays, and these are even smaller energy light rays. So, this is the idea which you have to have, and remember, highest energy also means the lowest wavelength everywhere. Highest energy means the lowest wavelength. So, series limit basically corresponds to the lowest wavelength that is present in that particular series. So, whenever we talk about series limit, do not think that limit means the higher value. So, it is a higher value of energy, but it also means the lower value of wavelength. So, series limit means the lowest wavelength in that particular series. Okay. So, let us see a question now. Find the ratio of shortest wavelength in Paston series to the longest wavelength in Balmer series. So, Paston series basically means all transitions to n is equal to 3. Okay. And similarly, Balmer series means all transitions to n is equal to 2. Okay. Keeping that in mind, so they are asking us to find out the shortest wavelength in Paston series. Shortest wavelength corresponds to the maximum energy, and maximum energy means n is equal to infinity to that particular state transition. So, let us calculate that first. So, let us call it as lambda 1. So, I can write 1 by lambda 1 is equal to R into Z is 1, we are talking about hydrogen atom. So, into, so shortest, once again shortest wavelength means highest energy. So, transition from infinity to 3. So, I can write it as 1 by 9 minus 1 by infinity. So, which is equal to R by 9. Now, similarly, for the second case, they are asking us the longest wavelength in Balmer. Longest wavelength means smallest energy. Smallest energy corresponding to Balmer series would be the one which corresponds to transition from the immediate next higher state, which is 3. So, they are talking about the photon which is released due to transition from n is equal to 3 to n is equal to 2. And if I consider that wavelength as lambda 2, I can write 1 by lambda 2 is equal to R into 1 by 2 square minus 1 by 3 square, and simplifying this you get 1 by 4 minus 1 by 9 and 5 by 36. So, which is 5 R by 36. So, they are asking us to find the ratio of these two. So, all you will have to do is just divide them, and you would get, when I divide these two, I would get lambda 2 by lambda 1 is equal to 4 by 5. So, 9 ones and 9 fours, so 4 goes to the numerator, yeah, 4 by 5 you would be getting. They are asking lambda 1 by lambda 2. So, lambda 1 by lambda 2 is equal to 5 by 4. So, that would be the answer. Now, let us move on to the next question. So, here they are saying a hydrogen atom is excited through radiation of wavelength 975 angstroms. How many lines are possible in the resulting spectrum? They are talking about the emission spectrum once it gets excited and while it is coming back. So, what are the possible wavelengths in the emission spectrum? Calculate the longest wavelength among them. Okay, so that is the question that they are asking. So, they are saying that a sample of hydrogen is basically excited by using radiation having a wavelength of 975 angstroms. So, now first you will have to understand what 975 angstroms here corresponds to. How much energy does it have and which transition does it allow the electron to take place. Okay. So, 975 angstroms, when I convert this into energy, I would be getting 12400 electron volt angstrom by 975 angstrom. Okay. So, because we are writing in angstrom, I have added one more 0 over here. So, I hope you understand that. Now, when I divide this, the value here comes approximately to be some 12.75 electron volts, and you already know what 12.75 electron volts corresponds to, which transition does it correspond to. I asked you to remember few values for all transitions from the ground state, because we will be mostly dealing with ground state. So, that energy there corresponds to transition from 1 to 4. So, what that means is that by radiating or by making light of wavelength 975 angstroms fall onto the hydrogen gas, we can consider that, or hydrogen atoms, we can consider that the atoms get transitioned to the fourth state, 1 to 4 transition takes place. Now, the electrons are in n is equal to 4 state. They are asking how many lines are possible in the resulting spectrum, which means in the emission spectrum from there, how many possible lines are going to be observed. So, if I am if the electrons are initially in n is equal to fourth state and if they are coming back to ground state, so how many possible ways are there for that electron to come back to the ground state? So we have already discussed this, and the expression which we have derived earlier was n into n minus 1 by 2. So these are the total number of ways in which an electron in fourth state can come to the ground state, and all the intermediate transitions also will be included here. So when I calculate this, I would get 4 into 3 by 2, which is 6 possible ways or 6 possible photons will be emitted in the emission spectrum. Now calculate the longest wavelength among them. So now the electron is coming from the fourth state, and you need to now understand what is the longest wavelength that is possible. So first thing, longest wavelength, what does it mean? So longest wavelength also corresponds to the smallest energy. Now understand that the energy levels would be something like this. As we go higher and higher and higher, the differences between the energy levels also keeps decreasing. Now we have an electron here, and there are 6 possible transitions. You know what they are? 4 to 1, 4 to 2, 4 to 3, 3 to 2, 3 to 1 and 2 to 1. Now out of all these transitions, can you tell me, can you understand which would be the smallest energy transition? You can see that in the diagram itself, the smallest gap corresponds to the smallest energy transition. So, and the smallest gap here is between these two energy levels, which is 4 to 3 transition. So 4 to 3 transition has the smallest energy. So what they are asking you now is to find out the energy corresponding or the wavelength corresponding to that transition. So the wavelength corresponding to this transition. So I will once again use Rydberg's formula to calculate that. I would get 1 by lambda is equal to R into 1 by 3 square minus 1 by 4 square. So I get 1 by 9 minus 1 by 16. So you can evaluate that. I would be getting lambda is equal to, so here I have 7 and in the denominator 144. So the value of that would be 144 by 7R. So that would be the answer.